Hello students, in the previous lecture we had discussed the features of TCP and also certain numbering schemes that are used in the TCP segment, such as the sequence number and the acknowledgement number. Before we have a look at the actual working of the TCP protocol, it is better to understand the TCP segment. So as you can see in the slide here, we see the segment structure. Before that, the data unit in TCP at the transport layer is called as the segment. Uh, in case of UDP, we call it as the datagram, whereas in case of TCP, we call it a segment. So this segment gets the data from the application layer, which acts as the payload, and then attaches a 20 to 60 byte header. So the data along with the header forms a TCP segment. As you can see in the bottom diagram, the header structure of the TCP segment is shown, which has several fields, namely source port address, destination port address, and such. So let's try to understand the significance of each such field in the TCP header. So the first field is the source port address, which is 16 bits long. So in TCP at the transport layer, entities are identified by using port numbers. So when a TCP segment is being exchanged, the header should contain the first field, which contains the port address of the source. The second field is again a 16-bit field which contains the destination port address. Then this is followed by a sequence number, which is a 32-bit field, and this is a random number that is assigned to the first byte of the data contained in the segment. Okay, so the sequence numbers we have already discussed previously. During the connection establishment at the very beginning, we generate a random number and use it as the initial sequence number. So this is the next field. Then after the sequence number, we have again a 32-bit field number, which indicates the acknowledgement number, again which we have already discussed. This acknowledgement number indicates what is the next byte that it has to receive. Then excuse me, following the acknowledgement number, we have the header length field, which is of 4 bits. So with 4 bits of information, the range of values that we can represent is from 0 to 5. But here we need to represent it as 0 to 15, but the range of values we have to represent here is from 20 to 60. So the header length is measured in multiples of 4. So if the smallest value being 5, 0101, and the largest value being 15, which is all ones. So if the header length is just 20 bytes without any additional options, then the header length field will have a value 0101. And if the size of the header is 60 bytes, then the h length value will be all ones, which is 15, 15 for the 60. Or if it is any other value in between 20 and 60, the value is divided by 4 and stored in binary form. Then following this, following the 4 bits, we have a reserved 6 bits field which is used for future purposes, followed by 6 bits which indicate different flags. Okay, so this flags together is also referred to as the control field, which contains 6 different control bits or flags. At the bottom you can see these 6 fields. The first bit indicates whether the urgent pointer is valid. The second one indicates whether this segment is carrying an acknowledgement. Then the third bit indicates a request for push. Fourth bit indicates resetting the connection. Fifth bit SYN indicates that it is used to synchronize sequence numbers, and the last bit indicates that FIN indicates that it is to terminate the connection. Okay. At this point, we will not discuss too much into these flags. Later, as we understand the working of TCP, the significance of each bit becomes well known. Then, after these control field, we have a next field which indicates the window size. So this window size is very much important for TCP to implement flow control. So this field defines the window size of the sending TCP. Okay, so what is the size of bytes of segments that the sending TCP is going to send is shown in the window size. And again, as the value is 16 bits long, you can easily find out as to what is the maximum amount of data that can be sent. Okay, so it is nothing but 2 power 16 minus 1, which is roughly 65,000. And then we have the checksum field. The checksum field again is a 16-bit field, which is very much similar to the structure of the UDP. If you recall the checksum field in the UDP, again it is a 16-bit checksum, and it works with a pseudo header, the same pseudo header that we had discussed in UDP, where it assumes certain of the fields from the underlying packet at the network layer and includes them in the checksum calculation. After the checksum, next 16 bits or the last 16 bits of the header indicates a special value called as the urgent pointer, and this urgent pointer is used to point to the urgent data. So the payload in data might consider some specific data that should be preferentially treated, and this urgent pointer stores that offset. Apart from these regular fields in the header, the TCP header can also contain options as well at the end. The options, sometimes the options may be absent, in which case the header size will be 20 bytes, or it can have an options of up to maximum 40 bytes. Okay, so the options fields in the TCP segment will be discussed later. Once we have known the structure of a TCP segment, now we will see as to how a TCP connection is established, data is transferred, and then finally terminated. So if we contrast TCP with UDP, TCP is connection oriented, whereas UDP is connectionless. So before any data needs to be transferred, a imaginary path or a logical path between the source and the destination has to be established. So and then the segments that are created are transferred through this same logical path. Okay, unlike in the case of UDP, each user datagram can take an independent path to the destination, whereas in case of TCP, all the segments should pass through the same logical path. So now comes an interesting question. all of you know that uh, the TCP, which operates at the transport layer, obtains the services of its bottom layer network, which is the network layer, and the protocol implemented at the network layer is the IP protocol. And interestingly, this IP protocol is a connectionless oriented. So now comes the question as, when TCP is supposed to use the services of IP, which is actually a connectionless protocol, how can TCP be connection oriented? So this is a very interesting question. In case of TCP, what happens is TCP works at a higher level. So here TCP makes use of the services of the IP, but in addition to that, it provides additional features. Suppose, say, for example, uh, it finds that certain segment has been lost during transmission. Then what it does is it asks for retransmission. Okay, so when this retransmission is happening, this is complete. The underlying protocol IP is completely unaware of it. It just thinks that TCP is just asking for some new data to be delivered, and IP tries to deliver it. Okay. However, TCP has asked for retransmission of this lost packet. Or it could also so happen that because of the services of IP, the segments may arrive in an unordered fashion. So in this case also, again, TCP holds back all the segments until any previously or a missing segment has not arrived. Okay, and once all the segments arrives, this TCP is going to reorder them at the receiver. So these additional services are being provided by the TCP, and the underlying layer IP is completely unaware of it. And this is how TCP is able to provide a connection oriented service on top of a IP protocol, which actually provides a connectionless service. Now that we understood how TCP brings in reliability, we now look into how data is actually transmitted between the server and the receiver, or the client and the sender and the receiver. So this TCP, which is a connection oriented transmission, it requires three phases, namely connection establishment phase, where a connection is set up, then followed by the data transfer, and after the data is transferred, we have a connection termination phase. So we will look into all the three stages one at a time. So TCP is bidirectional and it transmits data in full duplex mode. Okay, so both the parties involved in communication can act as the sender and the receiver, and they can transmit data in both the directions simultaneously. But before the data can be transferred, both the parties, both the participating parties, the sender and the receiver, must initialize the communication and get approval from other party before any data is to be transferred. So what do we mean by getting approval? So say suppose a sender wants to send a particular data, then it has to ask the receiver saying that it should request for a connection, and then the receiver will negotiate on certain parameters as to what should be the bandwidth, what should be the size of the resource window, okay, how much amount of buffers have to be allocated on the path. All these are going to be negotiated, and only when both the parties agree, only then data will be transferred. So this process of establishing a connection happens by a mechanism which is called as a three-way handshake. Okay, so this three-way handshaking is illustrated in this diagram that we show here. Okay, so at the application layer we have a client process, and again at the receiver we have a server process at the application layer. So this process of connection establishment starts with the server. Okay, the server process on the right hand side sends a message to its TCP at the transport layer. Okay, so the client process and server process are working at the application layer, generating messages or the data, and then it is the job of their corresponding TCPs to deliver them as segments. So server process sends its data to the server TCP, and client process sends it to the client's TCP or the client transport layer. So the server program informs its TCP saying that it is ready to accept connections and moves into a stage which is called as passive open. Okay, you can see this dotted line. Now the server TCP is ready to accept connections from the client, and it starts listening for incoming connections. Okay, so unless a server process uh, doesn't start with a passive open, no clients can interact with the server. Okay, so now the server has indicated that yes, I can accept connections from your end. Now the any client during this time which wants to interact with the server issues a request for an active open. Okay, so why we call this as an active open is because in response to this active open, in response to this request, the server has to reply back. Okay, that's why we call it an active open. Okay, so this is more involved, whereas in case of the passive open, the server is just willing to accept connections and is just waiting for some client to set up a connection. Okay, that's why it's called a passive open. At this point, okay, after the client program issues a request for an active open, the TCP, participating TCP, start the procedure that is called as the three-way handshaking process. So now look at the segment here. Okay, it would be better if you could keep this diagram handy. Okay, maybe you could open your textbook and refer to the same diagram when I explain this diagram. However, I will be coming back to this diagram whenever necessary. So after active open, the client sends a first segment. Okay, this segment is called as a SYN segment. Okay, so this segment will not have any payload, it doesn't carry any data. And remember, we discussed that the control field will have 6 different flags. Out of the 6 flags, only the SYN flag is set. Okay, the fifth flag, as you can see here, what is written as yes in the black shaded portion in the segment, the fifth bit which indicates the SYN flag is set. By set we mean that the bit will be set to the value 1. So once this SYN flag is set, it means that the client wants to set up a connection. Okay, so SYN stands for synchronization of sequence numbers. Okay, so for data to be transferred, the sequence numbers and the acknowledgement, there is a requirement for synchronization between sequence numbers and the acknowledgement being sent by the receiver. So what the client does is, apart from setting the SYN flag, the client chooses a random number and calls it the initial sequence number. So in our example, The initial sequence number is 8000. A SYN segment, okay, so a important thing is that it cannot carry data. It is quite obvious, as because unless the connection establishment is not over, TCP does not allow for data transfer. Therefore, a SYN segment cannot carry data, but it consumes one sequence number. Okay, so the next time the client is going to send another segment, it cannot use the same sequence number. For example, in our case, the initial sequence number is 8000. So next time, whenever a new segment is sent from the client, it should choose the next sequence number, which is 8001. So again, an important thing is a SYN segment cannot carry data, but still it consumes one sequence number. So once this segment is being sent to the server, in response to this, the server has to do two things. First is, it should acknowledge the receipt of the SYN segment that was sent from the client, and at the same time it should also send a request for opening another data connection in the opposite direction from the server to the client. Remember, we said TCP offers full duplex communication. Okay, communication in both directions. So to achieve this, the server will send a special segment in which two flags will be set. Okay, the SYN flag and the acknowledgement flag. This segment, as I said earlier, has a dual purpose. So first, with regard to the SYN segment, this acts as a SYN segment indicating that it wants to start a connection from the server to the client, okay, in the opposite direction. And at the same time, the server also acknowledges the receipt of the SYN segment sent from the client. So how is this achieved? This is going to be achieved by setting the acknowledgement flag. So if you look at the diagram here, the acknowledgement number is 8001. If you recall the definition of an acknowledgement number, the acknowledgement number says that what is the next byte that it has to receive and how many bytes it has received so far. So in the diagram here, the acknowledgement number says 8001, which means that it has received bytes up to 8000, and the next byte it has to receive is 8000. In other words, it is saying that I have received bytes up to 8000. And at the same time, similarly, the server will also choose a initial sequence number from its side. In this example, it is 15,000. And then it also needs to define the receive window size. So the server, in response to the client's request for opening a connection, it should inform saying that okay, this is the size of my receive window. Okay, the concept of receive window is very much important for bringing in flow control, that we will discuss later. Okay, flow control is preventing a fast sender from swamping a slow receiver. So for this, the server says that I can receive my receive window size is 5000 bytes. Means I can receive segments up to 5000 bytes, okay, not larger than it. Then you can also see like in the case of the SYN segment, the second segment also, the SYN plus ACK segment, it cannot carry data, but it does consume one sequence number. Okay, in this case also it is 15,000. So once this SYN-ACK segment is received by the client, okay, the client gets the acknowledgement for its request for connection, and now the connection is open. But at the same time, the client should acknowledge the request from the server side for a connection establishment. To achieve this, the client sends the third segment. If you see this, this is just an ACK segment because only one flag, which is the acknowledgement flag, is set. And if you see the acknowledgement value, it is 15,001, which means that it has received bytes up to 15,000. Okay, and also see its sequence number. The sequence number is now 8001. Okay, the next number after 8000. And it is also indicating to the server that its receive window size is 10,000. Okay, at a time it can receive a segment of 10,000 bytes. An ACK segment, if carrying no data, consumes no sequence number. Okay, so sometimes because a connection is being set from the client to the server just by the two stages, it is possible that data can be sent in the third segment itself. But if the data is not sent in the third segment, then there is no sequence number. Okay, so by exchanging these three segments, the connection has been established between the client and the server, and because these three segments are involved between the client and the server to establish a connection, we call this a three-way handshake connection establishment. So before we go to discuss the data transfer, we have a issue with regard to this connection establishment, which is called as the SYN flooding attack. Okay, so this comes to the security aspect. The TCP protocol is susceptible to a serious security problem called as the SYN flooding attack. So what do we mean by this SYN flooding attack? So in the SYN flooding attack, the fake clients, okay, so by fake clients we mean those clients that are not authenticated. Such clients which are trying to masquerade as someone else, and they start sending SYN segments to a particular server. Okay, as you know, a SYN segment is a request for a connection. So when the server receives several such SYN segments requests for connections, in response to these requests, the server allocates the resources for these connections. Okay, it will set aside some amount of buffer. Okay, it will set the bandwidth parameters and such, and it sends back a SYN plus ACK segment back to the fake client saying that I have accepted your connections. If the attackers are able to create large such fake requests, then they may render the server unusable because the server has allocated all its resources to these fake clients, and now if some valid client requests for a connection establishment, they will be denied the service, and hence valid clients cannot request for connections. This renders the server unusable. This kind of an attack belongs to a group of security attacks that we call as denial of service attack, or in short a DOS attack, where an attacker monopolizes the system and renders the system unusable by other clients. So how do we cope against this? There are several strategies. Okay, one such thing is to impose a restriction on the number of connections. Okay, so whenever the number of connections go beyond a particular threshold, 60%, the server will say that I will not accept more connections. Or we can have some authentication mechanism which will decide whether a client that is requesting for a connection is valid or not. Typically this is used by either validating an IP address or by using cookies. Okay, so this could be a possible venue for attack, which is called as the SYN flooding attack, which may render the server unusable. So this is with regard to the first stage, which is connection establishment.